In this video, we're going to describe the properties of giant covalent molecules, looking at diamond, graphite, graphene, fullerenes, and polymers. In diamond, each carbon is bonded to 4 other carbons. This forms a rigid structure which makes diamond very hard. If you wanted to break the structure, you'd have to break the covalent bonds. Diamond has a very high melting point. This is because covalent bonds are very strong, so it would take a lot of energy to break those bonds, therefore needing a high temperature to break those bonds. Diamond doesn't conduct electricity as it has no delocalized electrons or free ions, and you need something which can carry a charge to allow you to conduct electricity. Graphite is arranged in layers. The layers are held together by weak intermolecular forces. This means that the layers can slide over each other, which makes graphite a good lubricant. It's sometimes used on things like bike chains. In graphite, each carbon only has 3 bonds rather than 4. This means that each carbon has a delocalized electron, as it's only got 3 bonds rather than 4. So where that 4th bond is, there would be a delocalized electron instead. This delocalized electron can move freely throughout the structure, therefore it can carry a charge, which means graphite is able to conduct electricity. As graphite has still got 3 covalent bonds, it would still have a high melting point for the reasons we looked at a moment ago with diamond. Graphene is a single sheet of graphite, so we can say it's a single sheet of carbon atoms. As each carbon in graphene only has 3 covalent bonds rather than 4, it will be able to conduct electricity for the same reasons as we discussed as graphite a moment ago. As graphene is only single layer thick, it is extremely light and flexible. Fullerenes are hollow molecules of carbon shaped into balls or tubes. As each carbon usually has 3 bonds rather than 4, it means each carbon has a delocalized electron, so it can conduct electricity like we discussed with graphite. Fullerenes can be used in medicine. They can be used to cage other molecules, which means they can be used to deliver drugs to where it is needed in the body in a controlled way. They also have a huge surface area, so they make great catalysts. Catalysts are added to the fullerenes as they have a bigger surface area. Fullerenes are also used as lubricants. They can be coated on machine parts to reduce friction. You can see how the ball-shaped fullerene would make a good lubricant because 2 surfaces could roll over multiple of these molecules, a bit like if you had 2 metals between a series of ball bearings. Carbon nanotubes have a high tensile strength. That means they don't break when stretched. So they can be added to other materials to increase their strength without adding weight. For example, they can be used to strengthen tennis rackets. Nanotubes are very small and conduct electricity, so they can also be used in electronics. This is an example of a long polymer chain. Polymer chains typically have very high melting points. This is because the molecules are very large, so there are lots of intermolecular forces between different molecules. If you've got lots of intermolecular forces between different molecules, that means a lot of energy is needed to overcome these forces, meaning that they are often solids at room temperature.